Welcome back, everyone. So today we're diving into something incredibly elegant. We're looking at a sleek, fundamental mechanism that's operating at the very core of modern AI. It's called the Matrix Transpose. Now, I know what you're probably thinking. Math can sometimes feel, well, a bit dry, but absolutely not today. We're going to treat this like a high-end tech documentary. You're going to see how a really simple mathematical pivot is actually the secret engine making almost everything in AI possible. So let's just dive right in. Think about what happens literally every single time you type a prompt into ChatGPT, or really any large language model. Somewhere deep inside that massive architecture, millions of numbers are just flying around. But what you might not realize is that to process your words, a matrix quietly flips on its side. And it's not random, it's not like a coin flip. It flips exactly like a table of numbers being rotated 90 degrees, where the rows suddenly become the columns. And that one small, highly intentional flip, that is precisely what allows the model to compare your words against everything it knows, all at once, instead of doing it one painfully slow comparison at a time.
To really grasp this, let's just do a quick intuition check. Imagine a simple spreadsheet, maybe a table of student exam scores. You've got rows representing individual students and columns representing their subjects, right? Like math, science, and history. Now ask yourself, is there anything mathematically permanent about setting it up exactly that way? Like, if you decided to rotate that table, making the rows the subjects and the columns the students, does flipping that table change any of its actual information? Do the grades change? No, of course not. Literally zero information is lost. It's just the orientation that changes.
Section 1. The transpose, a simple pivot. Okay, let's see how this builds with some actual numbers to illustrate the exact mechanics of this pivot. Imagine a small matrix with 2 rows and 3 columns, 1, 2, 3 on top, and 4, 5, 6 on the bottom. To transpose it, we simply take that very first row, the 1, 2, 3, and we lay it down so it becomes the first vertical column in our brand new matrix. Then we take the second row, 4, 5, 6, and it pivots downward to become the second column. That's it. That is the physical mechanics of the whole thing. Rows just become columns. So the really crucial point here is what happens to the shape. Our original matrix was 2 rows by 3 columns, right? But after the transpose, our new matrix is 3 rows by 2 columns. The shape itself actually flipped. Listen, if you remember absolutely nothing else mathematically from this explainer, remember this one rule. Transposing a matrix that is m rows by n columns will always give you back a matrix that is n rows by m columns. Actually, let's test this out real quick. I want you to actively think about this for a second. If you're looking at a matrix that is exactly 4 rows by 7 columns, what shape is its transpose going to be? Just pause for a second. Try to visualize that flip. Exactly. It becomes 7 rows by 4 columns. It really is that straightforward. And honestly, it's fantastic if you're following the logic here because this one simple rule dictates basically everything else we're about to look at. Now, before we move on to how AI actually uses this, there is one super fascinating edge case, the symmetric matrix. What happens when you transpose a matrix that is perfectly square and symmetric, meaning it perfectly mirrors itself right across the diagonal? Well, transposing it gives you back the exact same matrix, completely unchanged. Symmetric matrices are literally their own transpose. It's a really neat mathematical quirk, but it actually shows up a ton in complex systems. Section 2. Why transpose matters, matrix multiplication, and dot products. All right, so we know how to flip a matrix, but why on earth does an AI engineer actually care? Like, why dedicate a whole explainer to this one move? Well, it all comes down to probably the biggest roadblock in AI engineering, the strict shape rule of matrix multiplication. To multiply a matrix A by matrix B, the number of columns in A absolutely must perfectly match the number of rows in B. But in the real world, your matrices almost never naturally line up that way. Taking 2 identical matrices and trying to multiply them usually just triggers a massive shape mismatch. But if you simply transpose one of those matrices, you flip its shape. And suddenly, those inner dimensions perfectly match. And boom, you have a valid multiplication. The transpose literally fixes the mismatch. And this exact same shape matching trick is how dot products work. Remember, a dot product measures how aligned 2 vectors are by combining them into a single number. To physically align them for that multiplication, you usually start with 2 column vectors. You take the first one, you transpose it into a horizontal row vector, and now it aligns perfectly to multiply against the vertical second vector. It's the exact same shape rule, just applied to the simplest possible case. Section 3. Scaling up. Neural networks and batching. Okay, let's scale this out of simple math and get into the realm of real, functioning neural networks and batching. Because this isn't just theory anymore. Inside a real neural net, every single layer is essentially just taking input data, multiplying it by a weight matrix, and spitting out an output. But your input data comes in as a feature matrix, rows for examples, columns for features. To make those multiplication shapes agree with the weight matrices, you are constantly having to transpose either the input or the weights. This is happening on almost every single forward pass. And it goes further. When we process batched data, meaning we're feeding the model hundreds of examples simultaneously for speed, the transpose is what allows us to rapidly reorganize that massive data orientation back and forth between one row per example and one column per example. It is the ultimate organizational tool.
Section 4. The climax. Transpose in transformer attention.
And that brings us to the moment where all this shapeshifting really pays off. Think about the famous formula inside the attention mechanism of every modern large language model. Attention scores equal queries multiplied by keys transposed. That little t attached to the keys in the equation, it's quiet, it's small, but it is absolutely 100% crucial. So here is the big intuitive question. Queries and keys actually start out as the exact same shape. Their rows are tokens, and their columns are embedding dimensions. Because they're the same shape, they cannot be multiplied directly. So why do we specifically transpose the keys? Can you deduce why this is the ultimate fix?
Well, here is the aha moment. Transposing K flips its shape, so the embedding dimensions finally line up perfectly for multiplication. But it does something far more magical than just fixing an error. By turning the keys sideways, that single multiplication instantly creates a full, massive grid of token-to-token comparisons. Every single word in your prompt gets compared against every single other word all at the exact same time. Without that transpose, you'd have to write painfully slow, line-by-line code loops. The transpose just bypasses those loops completely. It's brilliance.
Section 5. Conclusion. More than just a flip. Honestly, the next time you see a dot transpose call buried in some Python code, I hope you remember it isn't just decoration. It is a foundational reorientation tool. Just look at how far we've scaled in just a few minutes. We started with basic shape matching just to avoid error codes. That scaled into allowing dot products to measure vector similarity, which then scaled up to letting dense neural network layers process giant batches of data, which finally scaled into the legendary Q times K transposed, the very mechanism that lets language models actually pay attention to context, all from just rotating a table 90 degrees. Mind-blowing, right? In our next explainer, we are going to tackle two fascinating counterparts to what we learned today. We'll look at the identity matrix, which effectively does nothing at all, yet is completely mathematically essential, and the matrix inverse, which is all about undoing what has been done. Which leaves me with this final thought for you to chew on until next time. We've seen how matrices can transform, rotate, and reshape data, right? But if a matrix transforms space one way, taking your data and radically altering it, can we reliably find another matrix that undoes it completely, bringing everything perfectly back to the start? Think about that, and I'll see you in the next explainer.